My name is Kevin Noone. I come from two places in Stockholm, Stockholm University, Department of Applied Environmental Science, and also a place called the Stockholm Resilience Center. And then another part of me is at the Royal Swedish Academy of Sciences, where there's an office called the Global Environmental Change Secretariat. So we think about global issues and global environmental issues. I'm a scientist. I started off as an engineer. I'm kind of a mongrel. I never really knew what I wanted to be when I grow up, and still don't. So I started in engineering and moved on to atmospheric science and air pollution issues, and went into oceanography for a while, and ended up in what I would call Earth system science. So trying to look at the entire Earth system rather than just bits of it.
About more specifically now of the planetary boundaries, tell us the story, how the project started, how many people were involved.
Well, we had, turned out to be about, I think it's 28 people, or co-authors on the article. We started off at about 30 or so, from all different backgrounds. So we had anthropologists, historians, natural scientists, people that look at biology from across the spectrum, economists. And the main premise was we were looking at the environment in which all of our civilizations grew up. So if you look back in time, the last 10,000 years or so, environmentally speaking, have been pretty stable compared with the period before. And it's in that 10,000 years that all of our societies grew up. Round about, this is debatable, but somewhere around the 1940s, at the end of the Second World War, we humans became the dominant force driving much of the fundamental cycles on the planet. The nitrogen cycle, or the sulfur cycle, or to some extent the carbon cycle. We influencing the water cycle. So we became a dominant force, partially because of our population, but it's a product of our population, our size, and our consumption patterns. So we call that the Anthropocene, the epoch in which we're the dominant force, or at least a dominant force on the planet. And we asked the question, can we humans push the planetary system out of that stable state into a different state? And so then we asked the question, okay, well, what parts of the Earth system behave in a way that there might be like a tipping point? You can see very little change, and then you fall off a cliff, and you come to a new stable state someplace else. And that's when we started to go out and hunt and ask the question, well, how many of these potential tipping points can we identify?
Yeah.
So we didn't know how many of these boundaries we might find when we started, and we didn't know if we would be able to quantify them. And as it turned out, we think we found 9 of them, and we've been able to quantify 7 of the 9. Put numbers on where we think a boundary should be. Climate is one, but it has to do with carbon dioxide concentration. We have nitrogen and phosphorus cycle. We have ocean acidification as a boundary. We have freshwater extraction as a boundary. Land use change as a boundary. There's chemicals and chemical pollution.
We have all these boundaries. Then the next step after you identify and you quantify basically and try to get to this.
So we try to put a value on where the fence might be. And then another very important aspect of the boundaries analysis is that all these are connected to each other, such that we have a tendency to want to fixate on one thing at a time. So we might want to concentrate a lot on climate and climate change, or somebody else might want to concentrate on pollution of some sort. But all of these boundaries are connected to each other, such that the policy that you might want to pursue for one boundary will influence the others. And so you need to pursue those policies, keeping in mind how the other boundaries might behave.
The paper, the data was published, there was 2 or 3 boundaries that were already lost,
right?
If we can say it like that.
Biodiversity is one. We had one of the boundaries is global biodiversity loss. And we estimated that in terms of a loss rate, so extinctions per time. There's a lot of debate about whether that's a useful way to quantify a boundary or not, but that aside, we've gone way past that one in terms of our estimate of what a safe boundary might be. Another one is climate. We went over the climate boundary, I think, in the 1990s sometime, or maybe a little bit before, so relatively recent. The third one that we're well across is nitrogen, and the amount of nitrogen that we cycle through the planetary system. Now the question is, okay, we say that there's a boundary and we already know that we're across 30 and we're still here. There is a time element to this, to all of this analysis. So at the moment, for instance, we put our climate boundary, if you will, at 350 parts per million of carbon dioxide in the atmosphere. And we're close to 390 now. There is a success story, because one of our boundaries has to do with stratospheric ozone. And we were approaching that boundary. We were still well away from it. We were moving towards the boundary until the ozone hole phenomenon showed up, which was a huge surprise for the scientific community and everybody else. But as a result of that, and as a result of understanding what caused the ozone hole, the Montreal Protocol was signed, which eliminated the compounds that eat up ozone in the stratosphere. We've actually moved farther away from that boundary in the last decade or so.
Just to finish then, what do you think it will be the implications? Do you expect to have any policy implications over your systems, or if there's...
Yeah. Well, what I think, certainly I'm hoping, and I suspect a lot of my colleagues involved in the analysis are hoping as well, is that by presenting these boundaries as a connected set, that we can start lifting the policy and implications and decision support to a level that decisions aren't simply made piecemeal, like we normally make them. We look at one issue and we say we want to solve that issue right now and we ignore everything else. But that we start making our decisions with the knowledge that policies pursued, for instance, on climate or on biodiversity or on land use or some other area, are taken in a context, in a wider context. And I think that will make the ultimate decisions that we make a lot better informed and hopefully a lot better decisions. It's difficult at this point to point at any particular specific policy implication. I think that general policy implication of decision making in a connected framework is one that we're hoping will catch on.